Now that we have defined our conceptual model, let's go to the second step of our general modeling framework, which it means let's try to translate the conceptual model into a mathematical model. For doing this, we need to define the variables and properties that contribute to the water flow process. Let's define first the composition of soil. We already know that soil is a porous medium, composed of solid mineral, solid liquid, and air. And we may expect that the quantity of water, air, and solid will change between the different soil types. We further may expect that the quantity of water that fill the soil pores will also change in time. We may define the quantity of the different components in a given soil volume using mass concepts, volume concepts, or a mixture of both. In this table, for instance, several soil variables are defined that are related to this composition. Within this course, we will mainly consider the first 5 properties in the table. We will use the apparent bulk density, ρ, which is by definition the mass of the soil divided by the total volume, and that is expressed in kilogram per cube meters. We will use the symbol ρ in this class. Apparent density will be different than the real density of water and solids, which is defined as the mass of water or solid to the volume of water or solid, and that are indicated by the subscript W or S. The real density of solid is generally larger than the real density of water, and that's the reason why particles generally sink away when added to water. The real density of water and solid is generally higher than the real density of air. Since the total dry soil volume encompasses many pores and hence a lot of air, it will generally have an apparent density that will be smaller than the density of solids. The porosity of the soil is by definition the volumetric ratio of the pores compared to the total soil volume. The volumetric water content is the volume of water available in the volume of soil. This property has no dimensions, but to insist that we deal with volumetric ratio, we often add cubic meters per cubic meters as the unit of this property. Within this class, we mainly aim to have a model allowing to describe this volumetric water content in space and in time. With the previous definitions, we were able to define properties related to the composition of the soil, in particular the quantity of water that is present in the soil. Yet for determining water flow, we do not need to know only the quantity of water in a given soil volume, we also need to know whether this water is available and can be mobilized in the soil system. We therefore need to look to the energy status of the water in the soil. Indeed, if we want to transport water, it will consume energy. In a classical approach that is followed in this present course, we consider that water is situated in the meso and the microporosity of the soil system. The pores will therefore be small, and capillarity will develop in the soil system. In such cases, the water flow velocities will be rather small, and as a consequence, the kinetic energy component of the total energy of water particle in a soil will be small, and we can concentrate on the potential energy components to describe the energy of the water particle. A convenient and practical way to handle this potential energy can be followed by introducing the soil water potential. This soil water potential is defined as the work we need to develop to transport water from a given position in the soil towards a reference position somewhere else. This reference position could be a small and pure water reservoir situated at the level of the soil surface and subjected to a reference atmospheric pressure. If we want to transport the water from a given position in the soil to the reference position, it will consume energy, because water in the soil is subjected to many forces that eventually allows maintaining the water particle at a given position in the soil. The work that we need to introduce can be expressed in an energy per unit of mass of water, or per unit of volume of water, or per unit of weight of water. In the latter two cases, Units of water potential are simplifying to either the pressure units, hence Pascal, or length units, hence meters. We therefore can express water potential in pressure units or equivalent length units. In the latter case, it refers to the hydrostatic pressure of an equivalent water column. In soil hydrodynamics, we call this pressure the pressure head. The introduction of energy to mobilize water is needed because water in the soil is subjected to many forces. Each force contributes to a component of the soil water potential. Let's think about the forces that are exerted on the soil water particle. What are all these forces? Well, first of all, soil water like all matter on Earth, is subjected to gravity forces. A first component, psi-z, measures therefore the energy that should be introduced to transport a water particle from the soil to the reference water system that is situated at a different position in the gravity field. Very simply, if a soil water particle situates at 1 meter depth and the reference water body is at the soil surface, we should introduce the amount of work per unit of weight of water of 1 meter for transporting the water particle towards the soil reference system. This illustrates directly the practical use of the pressure head concept expressed in meters. In all cases, we can define a reference system, and the gravity component of the water potential is just the vertical distance in altitude between the location of the considered water particle and the origin of the reference system. Yet there are other forces that are exerted on the water particle in the soil. The particularity of many soil systems is that the pore space is not always completely filled with water. Soils are therefore often unsaturated with water, and in such cases, specific forces develop at the soil-liquid air interface that aim maintaining the integrity of this interface. It results in capillarity forces. These forces that aim maintaining the interface between water and air, and that result in the retention of water in small pores. Due to these capillarity forces, water in soil systems will be subjected to a negative pressure, a suction, and energy needs to be introduced to mobilize the water against these capillarity forces. This is the second component, psi-m. It is often referred to as the matrix head component or the capillary head component of the water potential. Another force that can be present in the soil is the hydrostatic force. If a water particle is situated in a saturated soil system, and this saturated soil system resides on top of an impermeable flow resisting soil layer, then a hydrostatic pressure can build up in the saturated soil water body. In such cases, the water pressure in the soil body will become positive, and it measures the pressure exerted by the water layers on top of the considered water particle. Hence, in a saturated soil water layer, a positive component of the water potential develops, Cp. This component will be absent in an unsaturated soil layer. Finally, there are additional forces that may affect the water status of a soil water particle. For instance, natural soil water will never be purely demineralized water, but will be loaded by ions, salts, or other constituents. If concentration gradients exist in the soil solution, then the thermodynamics of the system pushes these gradients to disappear, which results in a solid transport in the soil liquid phase. This goes hand in hand with the possibility to transport water particles in the opposite direction, and hence the appearance of an osmotic force. The osmotic force results in an osmotic force component of the water potential, psi-os. Another example of a force can be a force exerted by the solid phase itself. In most conditions, we consider that the soil solid phase is rigid and undeformable, yet in some cases, this hypothesis is no longer valid. For instance, in vertisoils, the soil solid is composed of specific clay that will swell and shrink in terms of the water content of soil. This swelling and shrinking will generate an additional force on the water particles included in the interstitial pores. This will result in a geostatical component of the water potential, Cg. To simplify our developments, we consider in this course only classical porous soil media. We therefore ignore the osmotic and the geostatic component of the water potential. We consider that no strong ion gradients are present in the soil solution, justifying the consideration the omission of the osmotic potential. We consider that our soils are rigid, justifying the omission of the geostatic potential. We also consider that our soils are isothermic, hence there are no strong temperature gradients, eventually introducing water movement due to buoyancy effects. In such cases, and considering height units, we can express the total water potential head as the sum of the position head, Z, and the matrix capillary suction head, H, and the hydrostatic pressure head. We denote this total pressure head with the symbol big H. We already stated that the pressure component, P, will only develop when the soil is saturated. The magnitude of P will directly and linearly depend on the thickness of the saturated soil water layer on top of the point of analysis. In case the soil is not saturated with water, the capillary head or suction head, H, will develop. The magnitude of H will depend on the desaturation state of the soil. Indeed, if the soil is very dry, soil water will mainly be situated in small pores. In these small soil pores, the capillary forces will be very high. If the soil becomes wetter, soil water will mainly be situated in larger pores. In these soil pores, the capillary forces will be less. Hence, capillary forces will decrease with water content. This is mainly due to the fact that an inverse relationship exists between capillary force and capillary radius, and that larger pores contributes to the soil water status when soil wets up. Yet the relation that exists between the soil water content and the capillarity head is not linear. This is also due to the fact that the distribution of soil radii in soil systems is not uniform. The capillary head often changes with a different order of magnitudes. And for practical reasons, we introduce the PF concept, similarly as the pH concept in water chemistry. The PF value is the logarithmic value of the negative soil suction head. The specific link that exists between capillary head, or the matrix suction head, and water content can be encoded in the so-called soil water retention curve. Indeed, when soil is not saturated, capillary forces will retain water in the porous medium, and extra energy, extra pressure needs to be introduced to extract this water. The curve is also often referred to as the soil drainage curve or the soil PF curve. It is a nonlinear curve and very soil specific. Actually, the shape of the soil water retention curve will be determined by the distribution of capillary forces in the RAV of the soil, and hence by the distribution of the soil radii within the RAV. The soil pore size distribution will be strongly controlled by the soil texture and the soil structure. So the soil water retention curve is therefore very soil specific, and it is a first specific soil hydraulic property that constitutes the soil hydraulic signature. An example of such a soil water retention curve is shown here. It generally is a sigmoidal continuous curve between a maximum value of soil water and the minimum value. The saturated soil water content, theta S, is here, and the residual water content is situated here. The residual water content refers to the quantity of water that remains attached to soil particles or that is completely immobilized when the soil gets very dry. We come back to the soil water retention curve later on in this course.